But now that I am here, it's really great to be able to talk a little bit about some of the work that's been going on at Ariel University since I joined that department in the fall of 2019. As the introduction mentioned, I was first a faculty member at the University of Rhode Island from 2010 until 2019 before I decided to move. And in that stage of life at the University of Rhode Island, our work in my research group focused heavily on cyclodextrin complexes and the use of cyclodextrin complexes as fluorescence-based chemical sensors. And then when I moved to the department at Ariel University, it was fortuitous that we immediately started working closely with a colleague of mine, Professor Flavio Grinspan, who has done outstanding work in the development of new bimain fluorophores. And so these are the general structures that I'm showing here, and I'll talk briefly today about how these fluorophores can be used for a variety of sensing applications, many of which we've published already together, and some exciting work that we're still working on. And so here I'm showing just 4 examples of this core structure substituted with different groups at the termini of the bimain, so dichloro or diproto, diiodo, or this trimethylsilyl acetylene. And you can see even that substitution has a marked effect on the photophysical properties of the resulting bimain solutions. And so we'll just talk briefly about what bimains are and what they've done. This bimain core structure, like I showed on the previous slide, was first reported in 1980 by Kosower and Pachevsky. And this core structure, which is this fused 5,5 membered ring, okay, with the dinitrogen connection here at the core, has been reported in both the syn isomer, so where the 2 carbonyl groups are located on the same side of the bimain structure, and as anti-isomers, where those carbonyls are located on 2 different sides. Interestingly, while bimain is highly fluorescent, and here we just show an example of a photograph of these solutions of these bimain fluorophores under photophysical excitation, we can see that it's been reported that the anti-bimain is almost entirely non-fluorescent. It has interesting properties which have not been extensively explored, which is that it can be phosphorescent at low temperatures. And so that's something that we're looking to explore further as well. Focusing now on syn-bimain in terms of the development of fluorescent chemical sensors, we can discuss that one of the reasons why this is particularly interesting for us is, as I mentioned, the fact that straightforward substitution at these positions, so again, chloro, proto, iodo, trimethylsilyl acetylenes, leads to dramatic changes in the photophysical properties, implying therefore that we have the ability to tune those photophysical properties through judicious choice of which substituents we put on these peripheral positions. Unfortunately, the reason why we think there's been very little bimain work done to date relative to other fluorophores is because the synthetic accessibility of these compounds has been challenging up until recently. And so it used to be that accessing those different derivatives, like I showed on the previous slide, would be an entire, let's say, PhD student's work. And I say until recently because, again, my colleague, Professor Flavio Grinspan, has focused on the development of novel methods to access bimain fluorophores compared to the previous method, which is shown in red of using chlorine gas, a base, etc. In several days, you'll get 12% yield of this diiodo compound. In the revised synthetic approach, they were able to get 30% yield of the diiodo in only half a day's worth of work, which is a substantial improvement from both the time and the resources perspective. Interestingly, in terms of accessing other structures, they also were able to demonstrate the ability to obtain the unsymmetrical bimain, that is the one which has through a slight modification of the conditions, get an iodo-chloro unsymmetrical bimain, which provides further accessibility to a variety of broader or extended fluorophores. And so what I will say, and so this combined, I think, pretty substantially with our work in the Levine group focusing heavily on the use of cyclodextrin chemistry. I just saw that my camera's not on. I'm trying to turn it on. Okay. No, it does not seem to want to work today. Okay. Nonetheless, our work in cyclodextrin chemistry in the Levine group focusing on the formation of non-covalent complexes inside that cyclodextrin cavity, and therefore the use and then the subsequent use of those complexes as fluorescent chemical sensors based on the ability to bind both a donor and an acceptor in that cavity simultaneously, which results in the formation or the ability to achieve proximity-induced energy transfer from the from the energy donor to that fluorophore acceptor. We were able to demonstrate good donor detection, good fluorescence detection of a variety of these donors, including some of these scaffolds that I'm showing here, including polycyclic aromatic hydrocarbons and aromatic amines and a variety of other class 1 carcinogens. We also, so again, combining really some of that access or some of the work that the Greenspan group had done in bimains with our ability to use cyclodextrins and develop fluorescence-based sensors, what we were able to then do is develop a variety of bimain cyclodextrin-based chemical sensors since we arrived at Ariel University, including what I'm showing here is the ability to achieve cobalt detection through the binding of cobalt to bimain, which is facilitated by cyclodextrin complexation, and then results, therefore, in the formation or the selectivity, good selectivity for cobalt, which we can see either as a color change in solution or in the solid state, or a fluorescence change as well. We were also able to develop analogously a iodine detection system, in this case using a different bimain scaffold in combination with cyclodextrin, which results in both colorimetric and fluorescence-based detection for that iodine. We developed a really exciting water-based water detection system for very low concentrations of water, and I will talk about this particular story in more detail on subsequent slides. And then finally, we've done some other water detection. We are really excited about both hydrogen peroxide and fluoride detection, which we're hoping to publish soon as well as a variety of other bimain cyclodextrin sorts of projects. And so, in particular, what I want to do is talk more about the ultra-sensitive, what we're calling ultra-sensitive water detection, precisely because it is so sensitive relative to other water methods. And it's all based on the scaffold that I'm showing here, which is the bimain ditriazole complex, which we can access relatively easily from the bimain diacetylene scaffold, which I showed previously. And so from the bisalkyne sym-bimain starting material, we can achieve a cycloaddition to access this particular scaffold. Once we have that scaffold, what we were able to demonstrate is that there's a highly selective quenching that occurs in the presence of copper, resulting in a strong decrease in that fluorescence of the bimain, which is also dependent on the concentration of the copper, and that adding water after we add that copper results in a rapid restoration of the fluorescence at relatively low concentrations. I'll talk about the quantitative limits of detection shortly. We can see here, though, visually even, a solution of that bimain under UV excitation is highly fluorescent. Copper addition quenches that fluorescence, and then subsequent water addition leads to a rapid restoration. We looked really carefully at quantifying how sensitive this system was for water, and found that our limits of detection were in the range of, shown here, as low as 0.8, times 10 to the minus 3% of that quantity of that percentage of water inside tetrahydrofuran is able to be detected using our copper bimain cyclodextrin system. It is moderately selective, the system, for water over other product solvents. So shown here is that the restoration of fluorescence for the water is pretty high, and for these other protic solvent. So for methanol and for ethanol, it is much lower, though there's certainly some restoration of the fluorescence that occurs. That's in parallel with this visual changes in the colors of the solution as well. How does this occur? What's our mechanism here? Well, our standard techniques of using NMR were a little bit complicated by the fact that the copper addition itself leads to significant broadening of all of the observed peaks. Nonetheless, we see particular broadening around the triazyl proton in particular, which suggests strongly that there's complexation and decomplexation of copper at that position. We see a pretty clear 1 to 2 complex formation based both on this kind of the calculations on these spectra, as well as other quantitative Job's plot analyses that occurred. So that is pretty much what I'm going to share, okay, as far as our work for today goes. I'll say that, when we think about what bimates have done and what they're capable of doing, we can talk about how they started from these very simple structural drawings in 1980, and that what we're able to do is develop and really functionalize and access these highly functionalized bimate scaffolds, including, this is one that I didn't talk about, but on the basis of this structure, we're developing hydrogen peroxide sensing based on the oxidative cleavage of these boronate esters, and then also developing high performance water detection on the same scaffold. So we see the same structure shown here. This compound 1 can either form a act as a hydrogen peroxide sensor, or can act as a water sensor, depending on the particular reaction it undergoes, and that those reactions are both result in strong fluorescence changes as well as strong colorimetric changes. What I'll say is that it's really been a privilege to work with my colleague, Professor Flavio Grinchman, as well as the variety of students both in my group and in the Grinchman group as well. And I thank the University of Ariel University for giving me the opportunity and bringing me to join their growing department and their highly research active system there as well. And with that, I would like to thank you both for your attention for my talk and for your patience in the time it took me to figure out my variety of technical challenges. And I would encourage you to follow us or the Grinchman group on Twitter as well for more updates on what's going on. So thank you so much to the organizers of this webinar and to you for your attention.